I'm Charles Wilson, Staff Product Cybersecurity Architect at Torque Robotics. This presentation will cover the static analysis perform analysis activity. This diagram shows the overall AVCDL training path. If you're taking this training, it's assumed that you've already completed the AVCDL overview training, and additionally, that you've completed the requirements taxonomy, security requirements, secure design principles, apply secure design, threat prioritization, secure settings, secure coding, static analysis overview, and static analysis established settings training. This training will cover the static analysis perform analysis activity. Before getting into how we perform the analysis, let's briefly review where it fits in the overall static analysis process. Here's the static analysis process, which we previously covered in the static analysis overview training. Our focus on this training will be on the second activity, that of performing the analysis. Drawing on the source code repository and using the settings specified in the updated build file, the static analysis tool performs a cybersecurity-focused static analysis of the element under consideration and generates output to a static analysis output file. As a note, it's recommended that JSON-encoded SARIF be used for this output. One might wonder, given that we've stated on multiple occasions that the analysis performance activity is hands-free, what the possible considerations could be. Even given its automated nature, there are some things worth considering when performing static analysis. Let's look at those. First, let's consider the impact on the results due to option interaction. As a reminder, options don't always act in isolation. If you're dealing with a strict rules-based analysis where every rule operates independently, then you're probably fine. If you're dealing with a static analysis tool where there's the possibility of interaction, say for instance with a compiler, you may have to adjust the options so that you're not getting unexpected outcomes. These may be either a cascade of additional issues that you're not ready to address, or the absence of expected issues. This is just the nature of using tools like compilers, which are intended to generate executable code, not be used for static analysis directly. The second thing to consider is the impact on the build process. Because static analysis is such a resource-intensive activity, there's a high likelihood that it will perturb the build process's timing or storage use. And so, the static analysis SME should work with DevOps to ensure that the build environment has enough headroom to be able to perform the static analysis activity. This is true regardless of whether we're talking about a build on the developer's machine or one on a dedicated build server. Also, keep in mind that because standalone static analysis tools backed by databases keep historical results so they can compare things not only across the entire body of the source code, but also across time, these tools have very large storage needs. The final aspect for consideration is the duality presented in the established settings activity. We don't simply have static analysis running on the build machine against the integration branch. We have the case where we're using static analysis against the developer branch on the developer's machine. We may also be using two different static analysis tools, or at least two different sets of settings. We need to ensure that as settings changes are made over time, they don't get out of sync. That covers the perform analysis activity of the static analysis process. Let's look at a summary. First and foremost, always consider the build system impact of static analysis. It can't be overstated that any disruption to the build system has a severe impact on the velocity of the development teams. And so it should be a priority to ensure that there is sufficient headroom for the static analysis activity to be performed. Next, if your organization is using multiple static analysis option sets, say one set for the integration branch, another for the development branch, or different tools for the build and developer machines, that you need to be sure that you're keeping these settings in sync. Finally, use SARIF for output when it's feasible. This is a kind of future-proofing, as JSON-encoded SARIF is easily processed by Python. This allows you to more readily ingest the output into issue tracking systems. It also can be used as feedback directly into various IDEs to facilitate mitigation by the developers themselves. For additional information and to get a more in-depth set of references, the Static Analysis Perform Analysis Procedure Tertiary document is available in the AVCDL GitHub repository. All AVCDL materials, both in source and distribution forms, are available on our GitHub site, as shown here. Because of the size of the repository, it's recommended that you either clone the repository or download a zip archive of it if you're not familiar with using Git. Instructions for downloading a zip archive are linked to on the repository's front page. Videos covering various aspects of the AVCDL are available on our YouTube channel, as shown here. It's important to note that all AVCDL materials, except for the introductory blog posts, are intended for product cybersecurity engineering practitioners. With this training complete, if you've completed the other trainings covering the static analysis process activities, you can proceed to the other trainings at this level. These include dynamic analysis, fuzz testing, and secure code review. Here are the references to the source material used in the creation of this presentation. They'll also be included in the video description. Additionally, this presentation source material will be provided on the AVCDL GitHub repository.